Hi, everyone, and welcome to the HelioCon seminar series. If you don't know me yet, my name is Brooke Stanislawski. The Heliostat Consortium, or HelioCon, is a 5-year research effort led by the National Renewable Energy Lab, partnering with Sandia, the Australian Solar Thermal Research Institute, and the Department of Energy's Solar Energy Technologies Office to develop and manage a national lab-led U.S. consortium to support research, development, validation, commercialization, and deployment of low-cost heliostats for concentrating solar power and solar thermal applications. Just a few housekeeping things before we get started. This seminar is being recorded and it will be made available afterwards on our website. Please stay muted when you are not talking, and feel free to put any questions you have in the chat during the presentation, and we can revisit those during the Q&A. Let's see, we will, depending on the number of questions that we get during the presentation, we'll save a few minutes at the end for additional questions. So now I will introduce our speaker. Thank you so much to Professor Kowalski for joining us today. Gregory Kowalski received his PhD in mechanical engineering from the University of Wisconsin-Madison. He is an emeritus faculty member in the Department of Mechanical and Industrial Engineering at Northeastern University in Boston, Massachusetts. He was an ABET program evaluator for mechanical engineering programs and is a fellow of ASME. He is active in thermodynamic and heat transfer research in nanoscale calorimetry using photonic sensors, as well as thermal modeling of laser beam propagation in medical materials for improving imaging techniques. His energy systems research includes developing tools for analyzing CSP and tri-generation systems and their integration with renewable energy systems, solar desalination, and integrating second law measures in the sustainability measure and energy system design processes. He developed and directed the College of Engineering graduate program in energy system integration until 2016 and the capstone design program from 1999 to 2019. So with that, I'll turn it over to you for the presentation.
Thank you, Brooke. I'm obviously Greg Kowalski. I would like to introduce also, and they are on the seminar, Professors McGulchy and Levendis, who are the PIs, co-PIs on the HelioCon grant that we have for bringing CSP technology to the Northeastern engineering curriculum. What we are trying to do is to introduce our students, practitioners to the challenges, rewards of CSP, how to analyze system performance, how to design the CSP systems, how to operate. And this is it's a challenge. It's complicated because it's not only a thermodynamic or heat transfer type analysis, but it includes optics, it includes controls, it includes the economic side of the equation. And these are all things that we're trying to introduce into a course, into a set of short courses geared towards the practitioners. And what I want to do is to describe some of our experiences, successes, things that we need to work on over the last year. We've offered the course once, and we're in the period of revamping it, improving it. So I want you to just think about these pictures and the amount of control, the solar plant in France that actually is built into the side of a building, and one of the solar furnaces that you have out on Tabletop Mountain, or Table Mountain, just behind facilities out in Golden. So with that, I want to tell you a little bit about Northeastern because this drives what we can offer to the CSP community, as well as giving us opportunities to involve large segments of our curriculum, as well as large number of students. This may sound like an advertisement for Northeastern, but my main point here is to indicate what we bring to the table and hopefully bring to our students. Northeastern University is a private R1 university. We're located in Boston. Many times people indicate that we are on the wrong side of the river, not in Cambridge. We like to view it the other way around. And most of my career and the careers of my two co-investigators has been to make sure that people don't confuse Northeastern with Northwestern. And I think we have turned the corner on that. We have approximately 32,000 undergraduate and graduate students. The graduate students are both at the PhD and the MS level. One of the unique features of Northeastern University is its cooperative education curriculum. Co-op is integrated throughout the program. It's when we interact with different people outside of the Northeastern sphere, it's difficult to get across our calendar. 90% of our students, undergraduate students, participate in the co-op program. Many of the master's level specialty programs also have a large number of people who go out on a 1-term or 6-month co-op. What you have to realize is that co-op, the students after their first year, they spend 6 months in the classroom, 2 terms. 1 term is at an accelerated pace, and then they go 6 months into a practical setting. What this means is we operate year-round. We do not have a, quote, summer off, if you will. And the facilities are maintained and used during that year-round operation. The co-op positions in the various industries, and our co-op students have gone from GE, Raytheon, to small startup companies, to jet propulsion labs. I think we've had 1 or 2 in years past at Sandia, and we're trying to improve that number with both Sandia and NREL during the period of this grant. But in the industrial settings, most companies actually have an identified position in the company that's related to co-op. They expect a co-op student to come in and actually do some work. All of these positions reflects the academic progress of a student. So in other words, if you have a student leaving their freshman year, they're probably going to have a low-level engineering type position, while students who have already had 2 co-op positions probably are going to be in a position of responsibility. What this translates to us and to the CSP program, we have a body of students at the upper class that are sophisticated, that have engineering experience, probably on the order of up to 1 year of actual practical experience. And this allows us to do many different things and sets our expectations higher. We also have certificate programs that are connected to the MS level graduate programs. One of them is the Gordon Engineering Leadership Program, where the students actually spend a year taking leadership type courses, and it rounds the students out and again gives them this second or more rounded outlook than just a, say, thesis or a graduate level program would do. In the Department of Mechanical and Industrial Engineering, which we are members of, we have approximately 600 undergraduate students, and I might be wrong on that number, then on the low side. Traditionally, material science is also within our department. When I first came to Northeastern, I found this strange, but over time, I found that it has worked. The department has 65 tenure faculty members, 20 professional teaching faculty members. And in addition, we have the engineering graduate programs that I've mentioned. We have one in energy systems, energy management, as well as the operational research. The mechatronics is also a key player in the CSP educational package we're trying to develop. As I said, I did not want to make this into an advertisement, but I wanted to illustrate the capabilities that we bring to the table. And excuse me, what I'm going to be presenting today, focusing on, is the CSP graduate course. And this is one objective of the Heliocon grant. But it's not the only item that we're bringing to the Heliocon community. Feeding into this graduate course, especially in terms of what students need, are the capstone projects and the capstone design course that spans 2 terms, essentially 21 weeks, that end in a constructed prototype. The students are given a problem. I'll describe 3 that we are currently working on, and a 4th that started us on the CSP tradition. And they're expected to actually build that prototype and do initial testing. We're also developing, as part of the Heliocon grant, short courses that are coming from the graduate course, but that are geared more towards practitioners. And I'll talk about that at the end of the seminar. We also have capabilities and actual programs within the university to foster undergraduate research projects as well as graduate projects. We also have a program, and I'll define the acronym later, LSAP, summer participation programs. And the last 2 summers, we have been successful in attracting students to do CSP-related projects. And we want to develop the co-op opportunities, as I mentioned. And if I move into the course, and as I start this, I forgot to say something at the beginning. If questions come up, please interrupt me. Turn on your mic and just stop me. I don't mind the interruption. Just have to make sure that Brooke keeps it in the time frame. What we did last spring was to offer a special topics course, Applications of Concentrating Solar Thermal Technologies. And I taught this. It was taught online in a seminar fashion. I'll mention more about that. Since offering this course, we have gone through the university approval process, and we now have a formal course, Application of Concentrated Solar Power. It will be offered in next spring, 2025. You can see the number. It will be offered on ground and online, and I will say more about that later. This is the opening slide that the students saw in the course, and again, it's to illustrate the integration of thermodynamics, heat transfer analysis, optics, the control of a mirrored field, and getting the students to understand the importance of the efficiency and how this is all an integrated problem. It's not just one discipline. And what I forgot, or not forgot, but have not mentioned yet, what are the economics? Obviously, if you look at some of the solar fields with the heliostats, this is not an insignificant investment. The course operation for the special topics course, it was conducted in a seminar manner. And please don't read all of this. I've highlighted the key points that I want you to take from it. Students were given reading and assignments, actual analysis to do, and we would meet once a week for approximately an hour and a half to 2 hours, depending on how many questions and or feedback that I needed to give them. I was trying to generate an open discussion of the readings. Did they agree with all the statements? What questions did they formulate? Sometimes based on homework performance, I would give short lecture materials to fill in background or to clarify the readings. The textbook that I selected was affordable, complete. I was happy with it, but it did require some additional background to fill in the analysis and the simulation part. In some classes, I would ask students to present their work. So as we started this course, I wanted them to understand the difference between the power and energy performance measures. And this is an offshoot, something I learned in the energy systems program. Students have been exposed to power and energy concepts. They don't seem to really integrate them, especially when it comes to viewing a power producing device that has to respond to loads and to provide supplies or to supply a guaranteed amount of supply, electrical energy over time. I wanted them to determine the benefits of CSP concerning not only power producing processes, but manufacturing capabilities. And this has to do with the high temperatures that we can achieve in these systems. In order to do that, you need to predict the incident solar radiation. You need to incorporate geometric optics. You need to predict performance measures of the heliostat field, as well as the thermal performance of the receivers. Finally, thermal storage plays a very large role in these matters, as well as understanding the economics. I've already mentioned the cost of these systems is not trivial. how can you make them pay? How can you get that 1, 2, even 5% improvement in performance through not only design, but operation and controls of the heliostat field that over a 25-year lifetime will make this much more economically appealing. And finally, it's the academic in me. There's the sustainability issues, especially related to the second law. I'm not sure of the background of everyone on this call. I'm assuming, I know we're all in the technical field, but the second law and the high temperatures that we get from CSP systems means we can produce much more efficient energy producing cycles. And that then leads to the idea of not only the economics, but the thermal-economic considerations, which is a great way to build in those initial capital costs. It's very ambitious. The textbook is by Gilles Lamont. It's 2022. It has, I would say, more of a European slant and more of an operator viewpoint, but it does provide a lot of the basics, and it presents it in a very readable fashion. And the topics that we actually covered are outlined here, and it follows basically the chapters in the book, except for chapter 6. And it's basically introduction, managing the solar resource. For example, this is predicting the incident solar radiation. However, it's more the forecasting and much more from an operation viewpoint. I come from analysis and thermal design. And it was a switch when you go through the book and realize the problems associated with operating these systems when you might have a nice cloud, clear day, but you have those high cirrus clouds that will affect the performance of the system. And how do you manage that? And how do you manage that when you have to connect to the grid or your manufacturing? Optics, I'll be referring to that throughout, as well as the solar receiver design. Simulation was something that I wanted to divert from the textbook. The textbook, it turns out, in chapter 4, does a very nice job of looking at the solar receivers and introducing numerical methods. But you still have the issue of selecting the right material. And how do you do the numerical method, especially when you have a transient source? And these are items that I wanted to emphasize some of the fundamentals. There are programs out there, and I'll say more about that later. You have the materials, the energy storage, and then the synthetic fuel production and the separation, conversion of carbon dioxide to high hydrogen-based fuels. These are items that, as you will see, we've been doing some of this in Capstone, in our Capstone design project, but at the same time, these are things directly related to the climate effects and how can we reduce the impact of that. Finally, the microeconomics, and I want to return to the manufacturing potential of concentrating solar power. this is what I wanted to accomplish in the course. Looking at where we were at the end of the course, the red highlight items are items that we briefly discussed. The yellow highlighted items, they were discussed, but no assignment was really given. And without having that assignment, without having it show up on the exams, students don't have the tendency to retain that information. And as you can see, we ran out of time to thoroughly do thermal energy storage and the micro and thermal economics aspect of this. The synthetic fuels production was another item that was just at the end of the course. And I'm putting this more because in the abstract, I said I was going to talk about our experience. And the reason for some of this was the students that came in had no background in the optics, geometric optics, the optics of the concentrating systems that you need in order to do the simulation. I also was surprised at the lack in their background of effectively combining convection radiative losses that are a key part of these solar receivers, and even the numerical methods. And I'll get into that more in a little bit. But one of the aspects of the mode that this course was offered, by having it in the seminar setting, I was able to go back, discuss these background effects, and as a result, we got behind in the amount of material to cover. This is something, again, from the syllabus, but what I wanted to indicate were, in addition to other references that directly approached heliostats, fields, and concentrating solar power, I also included a renewable energy and efficient electrical power systems by Masters. This is a book I came across. It's very good at illustrating and predicting incident solar radiation, as well as introducing non-electrical engineers to issues related to electrical power systems. In addition, I had put in basic thermodynamic books and the and heat transfer books, and I'm glad that I did based on what I saw from the students. Now, I'm sorry. What I want to do is go through some of the homework problems. And this is a problem that I gave the second week of the term. And you have to realize that in the second week of the term, and by the way, when I lecture, I tend to pace. Having me seated, you get more hand motion. So sorry if you see my hands pop up. This is problem second week of the term. We really haven't gotten into concentration factors. We haven't even gotten into the geometric optics. But this is a problem that I had used in the past that really illustrates a lot of the CSP challenges and what we need to be doing. This is a single point design condition. I'm giving direct incident solar radiation of a particular value. I'm asking them to determine the power output from the system and the first law efficiency. In this system, there's a working fluid that flows through the device. gets heated from an input temperature, and I've given them a concentration factor of 10,000. This is a term that is not really needed to solve the problem. And it presents a lot of interesting responses because students will go to the textbook, will go online, and will take and multiply the incident solar radiation by 10,000 and come up with ridiculously high temperatures. They recognize it. And when you guide them through how they should have solved the problem, there's a lot of head slapping, not by me. I give them an optical efficiency. And one of the things that I do is I indicate define your system and define it at the incident area that will avoid the need for geometric optics. They are given that optical efficiency and many of the other parameters, area, heat transfer coefficients, absorptivity, solar absorptivity, that I haven't included on here. So this is a very basic problem. You have a tube, fluid flowing through it, exposed to concentrated solar energy. And after the homework comes in, I go through and I indicate, here's the system shown in red dashed that you should have used. You have the flow of fluid coming in. It's going to have a temperature change. You have a change in enthalpy. You have the incident solar radiation on the incident area. It's not concentrated, as in the figure on to the right. The system is just looking at what comes in. And you have a heat loss that's going to be convective as well as thermal radiation. And what happens is when I move to the right-hand side, which is a side view, I can start to illustrate the concepts of what goes into a CSP system. You have to predict the incident solar radiation, as well as the angles that it's coming from, because that determines how much incident solar radiation actually enters the system. The concentrating system, how do you concentrate it onto a small area of the receiver tube? That's the main purpose of that concentrating system. It's going to depend on positioning controls. It's going to depend on the quality of your optics on your surface. You then have a thermodynamic analysis. What kind of working fluid do you have? And you then have to include the thermal heat transfer analysis, and again, the working fluids. And if you go back to the outline of topics covered, these are all the topics that we're going to be covering. And in this problem, it allows me to not only show them the benefit of the concentrating solar power, but it allows me to break up the various detailed items that you need to actually build one of these systems. I then ask them to go through. I'm sorry. I'm moving us so that I can see the slide. Homework 3 was using a solar prediction code. In homework 4, what I did was to go back to homework 2. And now we're starting to introduce simulation ideas. and the various aspects that go into those simulations. So I have them repeat homework 2 for their home location. We have a large number of international students. So instead of being Boston-centric, it's nice to be able to have them go back to their home location and actually predict the incident solar radiation for a given date, July 15th, between 11:30 and 12:30, bracketed around solar noon. And in this case, I'm asking them to include information that involves the cloudiness factor. This is a weather predictor. This is something that if you're operating one of these systems, you're trying to measure what is the cloudiness going to be in the next hour, 2 hours, so that you know how to operate your system and to integrate with the load demand and your grid, the grid supplier. I do simplify it by having them neglect the transient heating effects. But this is also getting at the idea of simulation. You no longer can just look at a single point. They're going to have to be looking at how much incident solar radiation do I receive for 2/10 of an hour, approximately 12 minutes. Then the cloud comes over. I have a lower value, pops back up. Think of these pretty cirrus clouds going over your heliostat field. This is exactly what would start to happen. Your main power input is going to drop down, then shoot back up and drop back down. So over the course of that 1 hour, they have several spikes. So now instead of one calculation, they have to go through and start to do the transient simulation, the time-dependent input, in order to calculate the total energy that's supplied. And one of the questions I'm asking them is to compare how much energy you would produce in this hour with the clouds versus if you assumed clear sky conditions. And again, this is getting at the difference between design and operation. The next problem, I really start to get into the idea of the heliostats, and I give them all the information highlighted. I do assume that the incident beam is parallel rays. It's an assumption, but it's a start. And the problem that I've given them are 2 heliostats, CSP tower, the receiver shown in red on the left, and they have to calculate the zenith, the elevation tilt for both heliostats, as well as the azimuthal. The first calculation is for noon. That takes away the azimuth direction. The second one is for earlier in the morning. And this was eye-opening to me for many reasons. And I'm going to move on because I think I'm way behind. Am I right, Brooke?
Yeah, just wanted to give you about a 5-minute warning.
Okay. The next problem got into the numerics. This is a figure from the textbook. It's a tube. I've given them all of the relevant heat transfer parameters, absorption, emission, emissivity parameters, but I've connected two of these tubes together. And the idea is take each tube as a small finite difference element and actually calculate what the temperature rise was. What I found from that was students had a real problem with applying fundamental numerical analysis. They're good or they're capable of running to a code, but they don't understand what goes into that code and how the codes work or what are the code's disadvantages. This is just a summary of the grade, and I assume this is going to be on the recording so people can go back to it. What I want to get to is when I did a survey, none of the students out of 16 in the class over a wide educational background had any type of geometric optics or ray tracing. This is critical. And it was confirmed through the homework, through the exams. Basic radiation theory, solid angles, iterative solutions, combining convection, radiation, and the geometric interpretation were all weaknesses. And homework 5 illustrated that. The numerical methods was a significant background weakness. Now, the good news is, one, we successfully are transitioning the course from me on ground to Professor Kuskun. I've transferred other energy-related courses with him. We have a great working relationship. He will be taking this and will be in a more of a lecture, 2 lectures a week setting. I think that will help avoid the time delays that I experience. He's had experience with our students, and we've had discussions about what to do with regarding the background weaknesses, and he'll address it. And we're expanding those background informations. The capstone courses. I really need to get through these, okay? 2 years ago, Professor Levendis can correct me, maybe it was 3. We started a project to convert plastics with the idea of using waste plastics, using solar energy to a synthetic gas using a pyrolysis method. And we had students in March in Boston on top of a parking structure with 20, 25-mile-an-hour winds, trying to manually keep this parabolic dish centered on the receiver tube. And to their benefit, we had 2 groups on this project. They actually did produce a little syngas, but they also showed us what needed to be done. Since then, we have expanded how many heliostat projects we have. One has automated the tracking, and this is one of the prototypes. Rebecca Mitchell actually visited us on the final capstone day. She saw phase 1 of this. We're now in phase 2. We've learned more about how to integrate these control systems and aiming it to a tower. We also did a deformable mirror with the idea of, can we simplify the control? Can we reduce the amount of power? And Ben Lynch, who is now a graduate student who's working with people at NREL and Sandia as part of the Gordon program, has a provisional patent on an idea of further concentrating the solar power. This is in phase 2, and we're looking at not only how to improve this, but what happens if we do a matrix of 4 of these mirrors. And then we went back to the pyrolysis using pine needles, which is a major issue with forest fires and organic matter. And the students are going to be designing a trough type system. These 3 projects, the students started in the May through July term. They're now on co-op. They'll be coming back in January to complete their prototypes and testing. What I want to say here are CSP projects are popular with students. Most renewable energy projects are. They've provided us an insight into what we need to provide students as far as academic background to participate effectively in these projects. And that fed right into the course development and the practical course. 2 of the students are currently submitted posters to the AAAS competition that's going to be held in Boston. And these are directly from those 2 heliostat projects. The second capstone sequence, in other words, the ones we don't participate with projects, have contacted us as experts to review their projects, give them initial design feedback. And I mentioned Ben being part of the capstone experience, moving to the master's program, the Gordon Leadership Program, and he also has a provisional patent. So I'm probably running out of time. Do people have questions?
Feel free to come off of mute to ask any questions you might have, or you can put them in the chat and I'm happy to read them. We have about 8 minutes for questions.
I know I just skipped several slides. Randy, you showed
All
up.
right, you called on me before I figured out how to raise my hand. Pretty good. That's great. You make a great straight man, as one of my favorite professors used to tell me. So yeah, great. I actually have 2 questions. One is, at the previous slide, you said that there was some interest in pursuing a co-op at NREL and Sandia, and it was not successful. I was going to send you an email about this, but since we're talking about it, in what way was it not successful? Sounds like a pretty cool idea to me.
Unsuccessful is a word that if I said, I was trying to avoid it. We've connected the appropriate people at both Sandia and NREL with our co-op professors, supervisors. We've had some interest from some students, but in the interim of getting an offer from either Sandia, NREL, they got another offer locally that was much more appealing.
Competing for the students.
So that's, yeah. One of the issues that we have, and it's a real sticky point. It's not a sticking point, it's a real challenge. Most of the companies that we deal with co-op have an identifiable, a reserved spot for a co-op student. And this is from year 1 to year 2, etc. Realize that when we move into the government laboratory domain, there's a higher level of transparency. There's a shorter time frame. You don't necessarily have a specified position. That means that it just puts us and the students into that, while we're waiting to hear, I got a better offer, I'm going with that. I don't want to make it sound like you're to blame or we're to blame. It's a challenge.
Actually, I think that's an enormously useful answer. From this side, I completely understand what you're talking about because of the way funding works around here and scheduling and whatnot. It makes sense. So
yeah,
that's helpful. That's helpful to hear. So thank you.
It's we've been on this grant for a year and a half plus. That's maybe 1 or 2 co-op cycles. I think just getting our co-op professors to the right people to contact and be in communication with on your end is a major advantage, is a major step forward, and it probably will work itself out in time.
Okay.
So,
Well, thank you for that. I have another question, but I see other people have questions, so let's let them go. Because
okay.
I'll catch up with you later. That's fine.
All right.
All right, yeah, I think Lindsay was next in raising her hand.
So Greg, just a quick question. I'm calling in from the Solar Energy Technologies office. I'm a fellow here. And I was just wondering if in developing your course curriculum, did you engage with any industry folks to determine what were, I guess, the biggest weaknesses there, or like gaps they're seen in the available workforce?
Half of your questions I can say yes. And again, thanks to Rebecca Mitchell, who she and I collaborated on a questionnaire, and she really reached out to that industrial section. This is more geared to the short courses that are being prepared, and the feedback that we have gotten, specifically as far as some of the content related parts of your question, what is needed. I would say our questionnaire didn't get into that depth level, but we definitely would welcome any type of input from the industry.
Thanks, Greg.
No, thank you for the question. Not an easy one.
All right, and I think Irene, you were next.
Yeah, thank you. So Craig, first of all, thank you for your presentation. I'm Irene Tseropoulou. I'm also faculty joining actually ASU. So we are planning for the fall semester to introduce a course at ASU, mainly focusing on the wireless aspects of CSP fields in consultation with Heliogen as well. So my question is very straight, like how open you are in, collaborations in terms of like seminars between the two universities, or if your course has some lectures that they are more seminar lectures, because I think that the two courses can very easily collaborate among each other, because my understanding is your course is more focused on mechanical engineering aspects, while our course will be more on communications, electrical engineering.
I would love to collaborate. I will speak for Professor Umet. I'm sorry, Kuskan. He definitely would be open to that type of collaboration. One of the I've taught, ran capstone for decades, as Brooke mentioned. We tried over that time to integrate electrical and mechanical engineering.
Mhm.
It's a challenge, but it's necessary. Mechanical engineers are very, very bad electrical engineers, and electrical engineers aren't great at some of the thermal analysis, but boy, do they really know sensors, they know controls. So it would be great to collaborate, and maybe we should take this offline.
Absolutely, absolutely.
Are
It's
you
something that I wanted to put on the table, because I think that general mechanical information coming from your course, like, introducing, I saw you have chapters that are related more to optics, chapters that are related pure to energy. I think that they will be very useful for electrical engineers, but also more controls related stuff that we are planning to teach. I think that they will be also useful for your students.
one of the courses, I'm sorry, I'm monopolizing this discussion. First of all, has Paul and or Tara introduced you to the Box Forum for posting course-related materials or course questions?
No, I'm not very familiar with what you are referring to.
Okay, maybe we should do, I'll send an email, give you
Sure.
Paul's name. That might be one forum. The second thing I wanted to say, one of our professors in mechatronics, Rafat Safai, has integrated CSP control theory as in part of their projects and in teaching the course and the PID. And he is doing some really interesting things, and that's another connection that you should probably pursue, or we should pursue.
Sure, absolutely. Thank you so much.
Okay.
Thank you for your questions. So unfortunately,
Yes.
we have to wrap up right now. But thank you again, Professor Kowalski, so much for the presentation.
Yes, I'm not used, my voice is going. I'm out of practice.
I'm going to steal the screen share for 1 minute just to remind everyone that the past seminar presentations, including this one, are available on our website up here, and the website has other resources as well. That our next seminar will be in January, so this will be the last one for 2024. But I hope you all have a great end of the year, and we will see you next year. Thank you.
Okay, thank you.
Thank you both. Really appreciate it.
Okay. Randy, thank you for showing up.
Yeah, my other meeting ended early, so I could catch the second half of it. I
Ah.
was very happy about that.
Good. I appreciate your comments. Always.
Great.
Okay.
Thanks. I've got some other stuff to talk to you about, but we'll do it later.
Okay.
All right. Thanks. Bye-bye.